In this video, we're going to cover the concept of circular motion uh, in regards to kinematics, so describing the behavior of circular motion. So earlier in our study of 1D and 2D kinematics, we saw that if the motion is always parallel to the acceleration, then the result is a change in magnitude of the velocity, but we didn't deal with a change in direction. Right? In other words, when we were looking at, say, 1D motion, in the case of something falling straight down, acceleration was acting in the downward direction, the motion was in the downward direction, and what we saw was that the object sped up, but it didn't change direction. And just now, in our study of 2D motion, and projectile motion in particular, we've seen that if we have the initial motion at some angle relative to the acceleration, then the motion is going to follow a parabolic path, a curved path. Right? And that's depicted in this picture here, where instead of shooting it straight up or straight down, we've launched it at, in this case, it looks like 20 degrees off of that vertical, and as a result, the motion is going to follow this parabolic pathway, curved path. So now let's consider what happens when the motion is always perpendicular to acceleration. You notice here that because the direction of the motion is changing over time, although the initial angle of the projectile with respect to the acceleration downward was, say, 20 degrees, that angle is changing over time. Right? So what we're going to do is we're going to consider a case now where we set it up so that the motion is always perpendicular to the acceleration. We've looked at always parallel to the acceleration. We've looked at various angles, and now we're going to take the other special case of motion that is always perpendicular to the acceleration. This comes into play in what we call uniform circular motion. Right? So imagine a object moving in a perfect circle. You can imagine that this could be a hockey puck on an ice rink that's been tied with a string to some center point. Right? So there's a spike in the center of the ice rink that's holding this string that's attached to this hockey puck, and we give it some initial velocity, and it just keeps spinning around and around and around this velocity without ever slowing down, if we assume that there's no friction on the ice. Okay, so let's take this scenario and let's calculate the average acceleration of this particle. Right? So first of all, let's understand why we say there's an acceleration at all. Right? We said the speed isn't changing. It's moving around at a uniform speed, but the velocity is a vector quantity. Right? And the acceleration of an object is defined as the change in its velocity divided by the change in time. But you can change a vector quantity like velocity in two ways. You can change its magnitude, or you can change its direction. Right? Here we've said that it has the same speed as it goes around the circle, so its magnitude isn't changing, but the simple fact that it's going around in a circle means that its direction is constantly changing. And so a change in direction means that the vector for velocity is changing, which means that there is some sort of acceleration. Okay, so to calculate the average acceleration, we need delta v, change in velocity, right? So we'll write v2 minus v1. So we're going to look at 2 time points. Right? At some point in time, it is particles over here, and its velocity at that instant is straight this way. But at a later time, at point 2, it now has velocity that is pointing this way. Okay, so we will do our vector subtraction, which we've noted before can be done as vector addition if we just flip one of the vectors, right? So it's v2 minus v1 is the same as v2 plus minus v1. Right? So we'll take v2, we'll take v1, right? We've moved them over here, but not rotated them. And we've flipped over v1 by 180 degrees. So applying the rules for vector addition, we take the inverted v1, place its tail at the head of v2 so that we get v2 plus minus v1, and the resultant vector, which points from the tail of the first vector to the head of the second one, from start to finish, we get delta v pointing straight down. Now, it should be noted that sometimes this is drawn this way to show that the change in velocity is the difference between where v1 pointed and where v2 pointed. So this is another way you can draw it, but for the purposes of doing vector addition, it's better to do head-to-tail method like this. So the important point here is that the delta v vector points straight downward. So since that's what gives the acceleration, the average acceleration vector, its directional quantity, right? Delta t is just a number. That means that the average acceleration is going to point straight down. On the other hand, the average velocity, right? And if you remember, the average velocity is just, when you take an average, you just sum everything up and divide by the number of things you summed up, right? So it's v1 plus v2 divided by the fact that we added two vectors. That gives us the average velocity vector. So v1 plus v2 in the head-to-tail method gives us a resultant vector, v1 plus v2, that points straight to the right. So the difference in velocity, the change in velocity, is a vector that points straight down, but the average velocity is a vector that points to the right. If we do this for not such a large change in position, right? Instead of looking back here, where we went from all the way over here to all the way over here on the circle, we do it for a finer slice of motion. And we repeat this whole process, right? Then you see that no matter what we do, as long as it's kind of symmetric around the straight up point, right, then the vector for the change in velocity is straight down, and the vector for the average velocity is straight to the right. If we take even a smaller slice, right, around 12 o'clock on the clock, by taking two time points that are closer together, right, only going from here to here, the delta v vector is smaller in magnitude, but still points straight down. The average velocity vector still points straight to the right. Notice as we take finer and finer slices in time, the average velocity vector, which we found for this scenario always points to the right, is becoming increasingly parallel to the instantaneous velocity vector for either of these points, right? At time 1, it was pointing just slightly up. At time 2, it's pointing just slightly down, whereas the average velocity vector for those two times is pointing straight to the right. At wider slices, that discrepancy is larger, right? So this is pointing much higher up, this is pointing much lower down. But as we take the time steps smaller and smaller, these are approaching to be very close to each other and exactly being parallel to v1 plus v2. In the limit that the time slice becomes infinitesimally small and approaches zero, the difference between the first velocity vector and the second velocity vector shrinks to nothing, and the instantaneous velocity vector at either point becomes parallel to the average velocity vector. Now remember, the difference change in velocity vector, the vector that represents the change in velocity, was straight down, while the average velocity vector is straight to the right. So these two are always perpendicular. And in the limit of the time slice going to zero, that instantaneous acceleration vector, which is just parallel to the delta v vector, becomes exactly perpendicular to the instantaneous velocity at each point, or the one point that matters, right? The point right in the middle. So at the moment that's pictured, the velocity is purely in the x direction, right? And the acceleration is purely in the y direction. But what about if we consider a moment later? Right? We've chose a particular point, 12 o'clock on the clock face, where the acceleration is straight down and the velocity is straight to the right, but a moment later, since it's moving in a circle, it would no longer be in such a nice condition. At that moment, all three vectors, the vector that points to where the particle is, the instantaneous velocity vector, and the instantaneous acceleration vector, all have both an x component and a y component. So in this case, perhaps the use of these fixed Cartesian coordinate systems, right? X always pointing to the right, y pointing up, z pointing out of the board, is not really the best choice for this problem. At least it's not the only choice. So let's at least consider moving to what's called a moving reference frame. Moving reference frame is one that doesn't just sit there and stay static, but actually moves along with the object that we're interested in. So as we move along with our object, what we'll do is we'll call the direction that's parallel to the velocity at that instant, the instantaneous velocity, to be the tangential direction. Right? We'll just create a new name. Instead of x and y, we're going to have a tangential axis, and the direction that's exactly perpendicular to that will be what we call the radial axis. So we have a tangential direction and a radial direction. A particular special case of this type of curved motion is what's called uniform circular motion. Uniform circular motion refers to an object that's moving in a circle, but without speeding up or slowing down. It's obviously changing direction, so its velocity is changing, but only the direction of the velocity and not the magnitude of the velocity is changing. For uniform circular motion, the acceleration is always in the inward radial direction, and it's called centripetal acceleration. The word centripetal just means center seeking, so it's a center seeking acceleration. The acceleration is pointed towards the center of the circle that the object is traveling in. For uniform circular motion, the acceleration has no component in the tangential direction. All of the acceleration is in the radial direction. So here's a key concept. Centripetal acceleration, the acceleration that's in the radial direction, only changes the direction of the velocity vector. It does not change the magnitude. That means it does not speed up or slow down the object. So the role of centripetal acceleration is to change the direction of an object. The role then of tangential acceleration is to change the magnitude of the velocity vector. That is, it's what speeds things up or slows things down, but it does not change its direction. Right? And so tangential acceleration is just the acceleration that we've studied in the past when we were dealing with just 1D motion. It's the type of acceleration that, if pointing in the exact same direction as the velocity, will cause the object to speed up, and if it's pointing in the exact opposite direction of the velocity, it'll cause it to slow down. Here I'd like to show you a quick derivation of this formula that we gave in the previous slide, that centripetal acceleration is v squared over r. This is not something you'll need to derive on an exam, so you're free to skip this entire slide if you like. But I like to show where things come from rather than just popping them up and stating them as given. Remember that v1 is perpendicular to r, and v2 is perpendicular to r. So notice for circular motion that the instantaneous velocity at position 1 is perpendicular to the position vector, r1. And at position 2, v2 is perpendicular to r2. Since v1 is perpendicular to r1 and v2 is perpendicular to r2, then the angle between v1 and v2 must be the same as the angle between r1 and r2. The two triangles that we show here are similar triangles, right, since they have the same angle between them. And therefore, we can write the ratio of the magnitude of the delta v vector to the magnitude of either one of these instantaneous velocity vectors has to be the same as the ratio of the delta r vector to either of these individual r vectors. Rewriting this slightly by bringing the v over to the other side, we see that the magnitude of delta v is equal to v times the delta r vector over r, or the magnitude of delta r vector over r. Now, remember that the average acceleration is defined as delta v over delta t. So we can take our expression here for delta v and divide that by delta t. And if we take that to the limit where delta t is going to 0, then we get a definition for the centripetal acceleration as being v over r, right? And then we have here a delta r over delta t. But delta r over delta t is our definition of v. So we end up with v squared over r as our definition for centripetal acceleration. All right, so now let's look at some consequences of this idea of centripetal acceleration changing direction, but tangential acceleration changing the magnitude of the velocity vector. So consider an object that's launched off a table, say, but purely horizontally. So initially, the only velocity it has is in the horizontal direction. The only acceleration that it experiences is due to gravity, and that's always in the vertical direction. So at the instant that the thing is launched, the velocity is purely horizontal, the acceleration is purely vertical, and therefore perpendicular to the motion, and therefore only changes the direction of the motion. Right? Remember that perpendicular acceleration or centripetal acceleration only changes the direction. But as soon as that direction starts to change, it's no longer being launched or no longer flying purely horizontal. It's now flying horizontally with a little bit of a downward component. Right? So it now has a small vertical component, and that acceleration due to gravity is no longer purely centripetal because it's no longer strictly perpendicular to the velocity. So as a result, the acceleration now has a tangential component as well as a centripetal component. So as a result, since the velocity is now pointing slightly downward, the perpendicular to that axis, the tangential axis, is now also slightly tilted. Right? It'll point like this, perpendicular to this. And as a result, the downward acceleration due to gravity has a component along both the tangential axis and along the centripetal axis, which means that both the magnitude and the direction will be changing. So at first, the component along the radial direction is small, and so the magnitude only increases slightly, but the direction is changing quite a bit. But over time, that vertical component grows and grows and grows as the ball continues to drop. And assuming that we neglect air resistance, the horizontal component, because there's no acceleration in the horizontal direction, continues to be constant. So we have an increasingly large vertical component of velocity, but a horizontal component that's staying the same. So the direction is increasingly more vertical. It's moving more and more towards the vertical. If you look at the downward acceleration due to gravity in this now greatly rotated coordinate system, where tangential is pointing nearly straight down, you can see that the tangential component of the acceleration is now substantial. That means that there's now quite a bit of tangential acceleration, and remember, tangential acceleration changes the speed of the object, but not the direction. So as we fly further and further along this parabolic path, the change in velocity vector goes from being mostly a directional change to mostly an increase in speed, in magnitude. Okay, so that covers the concepts involved in circular motion, the concepts of centripetal and tangential acceleration combining to give the total acceleration. In a separate video, we'll address an example where we apply these concepts to an object moving in a circular path.